We're going to go through the exact same process with example 2. It's just a bit of a different function. This is a rational function, whereas example 1 was a polynomial function. So to get the first derivative, we're going to need to use the quotient rule. So f prime g minus g prime f all divided by g squared. Work that out a bit. And there's our second derivative. Now, because it's a rational function, we need to treat it a little bit differently looking at the sign analysis. Nothing is going to make the top of this function 0. It's negative 26, and that's what it always will be. But the bottom, what do we have to plug into 2x minus 4 to make it work out to 0? Well, if you go off to the side, you may need to do this. You may be able to see it on your own. If we plug in a 2, we'll make the bottom of this function 0. So on the number line, if we plug in a 2, bottom of the function is going to be 0. When the bottom of a function is 0, that's infinity. We need to find out what this function is on either side of that, so I'm going to pick 0 and 3 as my test points. Substitute a 0 into the derivative. Now, I don't need to reduce this. I'm not concerned with the value of it. I'm only concerned with the sign. It's negative. Do the same thing with 3. And again, works out to a negative. So if we move on to b, increasing, this function is never increasing, it's always decreasing. Decreasing from negative infinity to 2, as well as from 2 to infinity. Didn't mean to put that c there. C is the extrema, the max or the min. Well, for the maximum and minimum to happen, we have to have a sign change on the derivative. We don't. So no maximum, no minimum. Second derivative now. So f prime, which is 0, g, which is 2x minus 4 squared, minus g prime. To do g prime, we need the chain rule. And f, all divided by g squared. Work this out what we can. What I'm going to do on the second term is this 2, and this minus 26. Those are what I'm going to multiply together because of what I'm going to do in the next step. So what we get out of that is 104 times 2x minus 4. Bottom, if we simplify those exponents, 2x minus 4 to the 4th. And now we can cancel off a 2x minus 4 from the top with the bottom. So our second derivative, 104 divided by 2x minus 4 cubed. Again, since it's a rational function for the second derivative, looking at that, what's going to make the top equal 0? Again, nothing, it's 104. What's going to make the bottom equal 0? 2, same as with the first derivative. But when the bottom is 0, function's infinity. I'm going to pick, in fact, the same numbers to test, but I have to test them in the second derivative. Again, doesn't matter the value, but this is going to be a negative number. Same process with 3. Here I have positive. Concave up, concave down. Concave up from 2 to infinity. Concave down from negative infinity to 2. The inflection points, we do have a sign change from negative to positive, however we don't have a 0 in between them. Okay, that is actually going to be a vertical asymptote, so we can't have a point of inflection at an asymptote because the function doesn't exist at the asymptote. So we have no points of inflection. The intercepts, again, I like starting with the y-intercept. Get the y-intercept as negative 0.25. Yes, decimals are okay. We're going to graph these. Decimals are easier to graph than fractions. X-intercept. What's going to make the top equal to 0? And we round it, x-intercept at negative 0.17. Asymptotes. Horizontal asymptotes, what's going to make the bottom of the function equal 0? Sorry, my apologies, that's vertical asymptotes. I mislabeled. So vertical asymptote at x equals 2. Horizontal asymptote, we have to take the limit of this function as x approaches infinity. Divide each term by the highest power of x. Cancel off what we can. Those terms that still have x left in the bottom will cancel off. So we have a horizontal asymptote at y equals 3. Now that we've got all these things together, we can go and sketch the graph.